Okay, today we'll be conducting a simple linear regression. The variables we'll be looking at are the number of miles ran in a month and the number of pounds before eating dessert. So first we go to Analyze, Regression, Linear. As you can see, I have the number of miles ran in a month in my independent section and the weight before eating dessert in my dependent section. I always clicked the confidence interval so we can have our confidence interval levels and push continue and push paste to bring up the syntax. The syntax is the best way to keep track of which analyses you run because sometimes you run so many analyses you forget which ones you've run. So if you have a syntax, you can keep track of what you've run, and you could also share these syntax with a research partner or anyone collaborating on a project with you. Just highlight the syntax, push the green run button, and you have your output. So things to look at. You want to look at your model summary. Your model summary tells you what your R value is and your R square value. Similar to correlation, your R value tells you the strength and direction of the association between the two variables. You can see it's a positive number, so it's a positive relationship, and it's at 0.984, which is a very strong relationship between two variables. We also have R square and adjusted R square. So these values are the squared value of R, with adjusted R square being a little bit more conservative. When you report these values, you can report both. Adjusted R square comes into place more pronouncedly when you have more than one independent variable, because it's able to be a positive number and a negative number depending if your independent variables are meaningful. Personally, I like adjusted R square, so I find that number to be a little bit more valid than the R square value, but depending on your discipline, you may want to go with whichever is most recommended for publication. You also want to look at your ANOVA table. This tells you if your model is significant. As you see, it's very significant because it's a lot less than 0.05. Then you want to go to your coefficient table, and this gives you a very detailed explanation of how much change happens when there's an increase in the number of miles ran in a month. As I mentioned, there's a positive relationship. So as a person runs 1 mile, there's an increase in the dependent variable by 1.165. So for every mile run, there is a 1.165 increase in the weight before eating dessert. It's a very interesting way of thinking, because you would think the more miles you run, the less weight you would have. However, we could interpret this as muscle being built. Maybe that's why there is an increase in of 1.165, but there's many interpretations. But to keep it simple, for every 1 mile increase when you run, there is a 1.65 increase in the weight that you have before eating dessert. So one thing I want to point out is very interesting is that if we run a correlation, as you see, I have my syntax for correlation. we see the correlation between the two variables. We see that they're significant, and we also get this 0.984, which is our R value. So when looking at one independent variable and one dependent variable, you will get a similar value as if you run a correlation in your model summary. So this is the way I would write up the results. A linear regression established that the number of calories from an ice cream cone could statistically significantly predict respondents' weight with the p less than 0.001. In addition, the number of calories from an ice cream cone accounted for 96.9% of the explained variability in the respondent's weight. So, key things to mention is that it is statistically significantly predicts because of our p-value, and also we wanted to talk about how much the independent variable explains the dependent variable.